Here's an introduction to radians. Radians are simply another way of measuring a turn. So we've chosen to use 360 degrees to represent a full turn, simply because 360 is a really convenient number that divides up in loads and loads of ways. There's no particularly good reason to use that. There is one system that uses 400 units to represent a full turn, and there's another system that uses 2 pi units to represent a full turn. I'm sure there are others as well. So radians represent a full turn with 2 pi radians. Therefore, 360 degrees must equal 2 pi radians, so 180 degrees must be the same as pi radians. So this gives you a whole load of common fractions of a turn, which you should know in both degrees and radians. So 180 degrees is pi radians, everything else scales from there. Pi by 2 is 90, pi by 3 is 60, pi by 4 45, pi by 6 30. So to go from degrees to radians, you divide by 180 and times by pi. To go from radians to degrees, you divide by pi and times by 180. Now, the reason why radians are a convenient way of dealing with turns or angles is because they simplify some of the formulae. At GCSE, you learned about how to deal with arc lengths and sectors, and we would have had theta out of 360, that's the fraction of the circle that I'm dealing with. So theta over 360 times 2 pi r, that fraction of the whole circumference, would have given me s. Well, now if I do theta out of 2 pi in radians times 2 pi r, the 2 pi's will cancel, so the formula for the arc length is really quite simple. It's just r theta when theta is given in radians. Similarly, for the area of a sector, at GCSE you would have done theta out of 360 to give you the fraction of the circle, and then it would have been that fraction of the whole area. So you would have done theta out of 360 times pi r squared. So if I swap from theta degrees out of 360 degrees to theta radians out of 2 pi radians, I would get theta out of 2 pi times pi r squared. Now if you follow that through, the pi's will cancel, and all you'll be left with is theta times r squared, or r squared times theta, divided by 2, where theta must be in radians. A common example of this is this kind of question here. You did see this at GCSE as well, so my rather wonkily drawn circle here has a triangle from the centre of the circle subtracted from it, and I want to find the area of this segment. So I've got pi by 3, which in other words is 60 degrees. So I can see that this bit is what I would get if I took this sector and subtracted this triangle. I know the area of a sector is r squared theta over 2, so that will be 4 squared times pi by 3 over 2, and I know from GCSE that the area of a non-right angled triangle is a half AB sine C, where C must be the angle between the two sides A and B. There's the formula there. So in this case that would be a half times 4 times 4 times sine pi by 3. It's just slipped off the page a little bit. So with only one line of working, all I need to do is drop that into my calculator, and I would have found that the area of that shaded segment was 1.45 square units.